based on the previous that we talk about the entropy, we talk about the internal energy. And also when you study the thermodynamics, we have entropy. That's right. For this term, we cannot measure or we cannot determine it the pure form. That's right. It's not possible to know the absolute value of the internal energy or entropy, but we can determine the change in internal energy or the change in entropy. That's right. We use calculate based on the change with respect to the change of state, which may be at temperature, at pressure, at the change in the phase, something like this. Okay, for that case, for the convenient way to calculate or to measure the change in specific internal energy and entropy, we have to choose the temperature, pressure, and the state as the reference state. We have to choose the reference state to calculate, because we cannot calculate the absolute value of S, absolute value of U like this. Okay, for this case, we have to choose the reference state. Okay, we give you some example. Right. For this example, we calculate the change of the enthalpy of carbon monoxide going from reference state measure, like following. Okay, we know, right, the carbon monoxide at 0 Celsius 1 atm to 100 Celsius 1 atm. What does it mean? This we check the enthalpy of carbon dioxide at 100 reference to 0 Celsius. It's equal to 2,919 joules per mole. And also the same, if we reference the carbon dioxide at 500 reference to 0, it's equal to 15,060 joules per mole. What does it mean? Because we cannot calculate the entropy at 0 Celsius, entropy at 100 Celsius, but we only determine the difference between two states. And mostly we choose the reference state at S equal to 0. For this case, for the convenience, we assign the value of the entropy at reference state is equal to 0 for the convenient way. That's right. That means entropy at 0 Celsius equal to 0. That means the 0 Celsius entropy equal to 0. And delta S from 100 to 0 is equal to 2,990. Or entropy from 500 relative to 0 equal to 15,000 approximately. Right. For this case, we only determine delta S, not S. But for this case, delta S1 equal to S1 plus S0 equal to S1 because S0 equal to 0. And also delta S2 equal to S2 because S0 equal to 0. Okay, for this case, we can read like the specific entropy of CO at 100 Celsius 1 atm relative to CO at 0 Celsius 1 atm equal to this value. This value is the entropy at 100 relative to 0 Celsius. So this is the reference state. Okay, for the example, we have the following table. That's right, the following table taken from the data for saturated methyl chloride. That's right, in the liquid state, vapor state at different temperature, different pressure, something like this. Okay, for this table, what reference state was used to generate this enthalpy? That's right. If I talk to you previous slide, the reference state enthalpy equal to 0. For question 1, you can conclude that -40 Fahrenheit, 6.878 PSIA is the reference state. That's right. This is the reference state. This is the first question. It's answered already. That's right. The reference state is at -40 Fahrenheit and 6.878 PSIA is the reference state because enthalpy equal to 0. Okay. The second one, calculate delta S and delta U for transition of saturated methyl chloride vapor from 50 to 0. That's right, 50 to 0. Okay, for this case, delta S equal to S at 0 minus S at 50. because this is delta S from 50 to, the 50 reference to 0, that means from 50 to 0, from 50 to 0, this is the first, is the second. That's like entropy at 0 minus entropy at 50. Okay. Okay, it equal to from 0. Okay. 202, that's right. 202 for this. You get this way. That's why this we use the reference, that's right. Okay, because entropy at 50 equal to at 50 equal to 202.28 minus 0. That's right. And entropy at 0 equal to 196.23 minus 0 already. Because this is reference to minus 40. It's also reference to minus 40 already. That's right, for the scale. Okay. And then you calculate the internal energy. Like internal energy. Internal energy from the definition of entropy equal to U plus PV. That's right, U plus P or delta S equal to delta U plus P delta PV, like this. And you can calculate delta U equal to delta S minus delta PV. That's right. This is delta S. PV is PV final minus PV initial. Right. And delta S equal to this value. Okay, this is delta S. PV. Right, from 0. This is from 0. So P from 0. That's right, S10. V from 0. Minus 50. That's right. 50 is this 50. Is 50. You get like this. And also we use the conversion unit from BTU to PSI. Like this. You get this unit that I use. Okay, what the assumption did you made in solving equation? For this case, we use the entropy independent of pressure. That's right, entropy independent of pressure. For I will prove this for the later slide. We talk about the property of the entropy volume with convert or with depend on temperature. The strongly depend on temperature, but slightly depend on pressure for the scale. For this case, the application of different state. If we talk about the steam table in the mean of the water, that's right. Table for water. We have liquid, vapor, that's right. Liquid form, vapor form. And also we have the sap and supersap, something like this. Sap liquid, sap vapor, and supersap vapor. I think you study this in detail in thermodynamics. Like if we consider like the P and T diagram of the system, we have the solid, like superheat, a vapor, and subpool liquid, liquid, saturated state, like this. Like the steam table is referring to triple point. This is the triple point, like this. If you consider a steam table or table for water, the reference state is triple point. That's right, the triple point, the pressure and temperature at triple point. Like for this example of the saturated steam, that's right. Temperature change, pressure, volume of water, volume of steam, steam may be vapor, that's right. Entropy and internal energy, that's right, internal energy. This is for sat liquid, that's right. Sat vapor. This is the entropy for sat liquid. This is the entropy for sat vapor. This is the entropy. The difference between sat vapor and sat liquid is the entropy for vaporization. Heat of vaporization. That's right. This is the heat of vaporization. This is the difference between the entropy of sat vapor minus sat liquid. We get the heat of vaporization. This from the steam table. And also sometimes you can separate in terms of pressure. That's right. This is the temperature. is volume, internal energy, and enthalpy also. It's an example of the steam table. And if the higher in temperature, higher in pressure, the vapor and sat vapor and sat liquid is maybe superheat steam. That's right, superheat steam. For that case, it's superheat steam. When this is the length of the superheat steam, it is a superheat. This is the sat liquid, sat vapor. That's right, sat vapor. We add for example, at 0.5 bar, that's right, 0.5 bar. At temperature 75, it's also like liquid. But if the temperature is greater than about 75, that's right, it is superheat. Nothing is. But at 0.1, that's right, it's also a superheat. That's right. Okay. And for 10, 5, 10, 1, 5, 10 is greater than 150, it's superheat. Lower than 150, it's sat liquid or sat vapor. Sat liquid or sat vapor. This is in terms of pressure. This is the sat temperature. This sat temperature, sat temperature, sat temperature. This is based on liquid. Sat temperature of liquid means the boiling point. That's right. The point that liquid is change from liquid to vapor. Like this in terms of all of this is superheat. That's right, all of this superheat. From the superheat, the sat it should be dew point because this is vapor form. That's right, this is the vapor form. The sat temperature is the dew point. That means the vapor condensed to liquid. That's right, vapor condensed to liquid. Okay, this is some, I will give some example. Steam table I collect from the book or the appendix of the book. Okay, this is some steam table. It's maybe sat liquid or subcool liquid. Subcool liquid means the liquid temperature lower than the sat temperature, sat pressure. Sat vapor, that's right, sat vapor. And superheat. Superheat means the vapor form that is higher than sat temperature or sat pressure. Like this. Okay, I will give you some example for calculate the steam table. Okay, for the first example for the steam table, determine the vapor pressure, specific internal energy, specific enthalpy of saturated state or sat vapor. You can see that the table. This is volume, internal energy, enthalpy, and also you can calculate sat temperature. For this case, you can calculate sat pressure. Right. In this table is the sat pressure, is the sat temperature, and it is the sat enthalpy, sat internal energy, sat volume. That's that. Okay. And this is the enthalpy, internal energy, and volume at temperature is greater than sat temperature, greater than sat temperature. It's maybe at 50, at 75, at 100, and 150, like this. But at this at sat temperature, sat pressure. Okay. This is all the superheat for this. Okay. Like for this, determine the vapor pressure, specific internal energy, specific volume, pressure. Right? Yes. Of the steam, this is the sat vapor at 133.5 Celsius. And the second one show the water at 410 bar is superheat. And determine the volume U and S of the liquid relative to the triple point. For this case, the relative to the triple point, this is the steam table. You can calculate it from the steam table. Because the steam table is referring to the triple point already. Because I talk to you, we cannot calculate U, we cannot calculate S for absolute value. We can calculate delta U and delta S only. But in the steam table, it's related to the triple point already. That means the steam table is delta S already. That's right, delta S already. Okay, and the third question shows U and S for superheat steam depends strongly on temperature and relatively slightly on pressure. For this case, you can check from the steam table. It's correct or not. Okay, the first one, you know temperature, and you know this is a set vapor. Okay, for example, I already this from the steam table, like this. Oh, you know temperature, that's right. 133.5. What is the only volume, intensity, and entropy? For this case, we call it set vapor. That's right. The volume of steam. This is steam. This is liquid, but for this case, we only steam. This is the intensity of the steam. This is the entropy of the steam. That's right. Okay. Like this. And the second question show that the temperature of water at 410 bar is superheat. Okay, is superheat or not? Right. For this table can help you. This is 0.5. That's right. For this for 10 bar. Okay. 50 is liquid, 75 liquid, 100 liquid, 150 liquid. Okay, 400 is greater than this. That's right. It's greater than this. This 400 is superheat. It also you use this table for the 10 bar for 400 is superheat. Okay, this is clear. The water at 410 bar is superheat steam. That's right. Superheat steam. Okay. And this is the enthalpy, intensity, and volume and temperature. You can look at this table. All right. For 400, this 400. This is the enthalpy, intensity, and volume. And temperature, this is the set temperature. Like this. Okay, this is the answer. Okay, and the last question. Show that U and S is strongly depend on temperature, but slightly depend on temperature. For superheat, I will check. Okay, for this table is a superheat table. Superheat table. If we check the enthalpy when 400, 450, 500, you can see that the enthalpy is changed strongly. That's right, changed strongly. If you compare between the change in pressure, it's slightly different. From 0 is 3,200 SD, 0.1 3,200 SD, 0.5 3,279, and 10 is 3,264. It's slightly different. That's right. It's slightly different based on change in pressure, but it's strongly different. It's change in temperature. And also, if you check the enthalpy and internal energy, strongly also, it's quite the same, right? And volume also, that's like 71. Okay, two on this. We can conclude that from this table, enthalpy and internal energy strongly depend on temperature, but slightly depend on pressure. Because you can see that from this table, when increase in temperature, the value of enthalpy or internal energy increase strongly with temperature. But for the pressure, right, when increase in pressure, enthalpy and internal energy decrease slightly with pressure. Okay, you can use this data to check the difference of internal energy and enthalpy at pressure change or temperature change. And also we conclude this table up to you already. Right. And also I think when you study in the thermodynamics, you maybe use the the database or the reference from the World Wide Web. Also, I check. I'll show you. Maybe you can check. Okay. For this case, I give you some example for the National Institute of Standard and Technology. Institute of Standard and Technology. Okay, for the first. Okay, for the first, question 1, that's right. You can use the table that I give you in the textbook, or you can use the reference from World Wide Web. Okay, from the first, we calculate the vapor pressure, specific internal energy, specific entropy, such stream at 100, such stream, okay, at 133.5 Celsius. For this case, we have this property of fluid, we choose water like this. This is for webbook.nist.government chemistry fluid. Like this is the National Institute of Standard and Technology. Okay, the fluid property. We have a lot of fluid in this, that's in the database. For this case, the steam table in water. Temperature in Celsius, pressure in bar. Sometimes you have to choose the unit. Energy in kilojoule per kilogram. Okay. Right. For this case, we choose the saturated. This may be temperature increment. Okay. We calculate at temperature 100 and okay, 100. 1, 1, 2, 4. Okay, we have only 0.5. Okay. This show you this temperature and pressure. Right, the pressure is 2.99 bar. It's about 3 bar. That's right. It's about 3 bar. It is it. And also, we would like to calculate the volume. For this case, we use the steam. That's right. 0.606. It's close to the value from steam table. Yeah, 0.606. How about internal energy of the steam? Internal energy, you can choose this. You can choose internal energy. Okay. 2,543. You check with the steam table. Okay, it's close together. And the last one that we would like to enthalpy. For this case, we calculate at 133.5. 2,774. Okay, correct. You can use this. You can use this for estimate the steam table. Okay. It's the same value, right? I talked to you for the first question. Yeah, it only gives you some example. Okay, the next example, right? We will apply the energy balance. Example 7, we only use the steam table. But example 8, we apply the energy balance and also you use the steam table as the information for the energy balance. Okay, for this case, we have steam at 10 bar absolute with temperature of 190 of superheat. What does it mean? The superheat. That means 190 is higher than the sub vapor. It's fed to a turbine at a rate of 2,000 kilograms per hour. The turbine operates is adiabatic. That's adiabatic means Q0. The meaning of adiabatic means that there is no heat transfer between system and surrounding. That's not Q equal to 0. And the outlet It's saturated stream at 1 bar. This is the outlet. Inlet is 10 bar. Outlet is 1 bar. Calculate the work output, right, of the turbine in kilowatt. For this case, we neglect kinetic energy and potential energy. That means delta E, P, E, K equal to 0 and Q equal to 0 based on adiabatic. Okay, for this case, delta S equal to WS minus WS, or WS equal to minus delta S. M in, M out equal minus M equal to S out minus S. Okay. Okay, for this case, we have to calculate the inlet. The inlet is superheat S900 is greater than for this case. For this case, you have to find what is the set temperature at 10 bar. That's right. At 10 bar. This is 10 bar. The set temperature is about 180. Okay. The temperature inlet should be 180 plus the superheat. Superheat is 190. Okay, this is the inlet temperature. Inlet temperature is 370. That's right, 370. 10 bar. That's right. This is the data for 10 bar. But 370, it is between 350, 400. You have to interpret. That's right. The enthalpy is between this value. You have to interpret this. You have to interpret this. For this case, okay, we have S. Sorry. 319,559, 3264. And temperature, we know this is the 50, 400, and 470. X value. We have to calculate, interpret like this. You have to calculate X, okay. It may be X minus 3159 divided by 3246 minus 3159 equal to 70 minus 350 divided by 400 divided by 350. Okay, from this you can calculate X, right? You can rearrange this equation and then you can solve for X. This is the interpolation based on linear relationship. Okay, and then you can interpolate S approximately. That's right. 3,201 kilojoule per kilogram. Or you can use the standard table from website that I showed you previously. Okay, you know the entropy inlet. Entropy inlet is relative to triple point already. That's right. Okay, the outlet. The outlet is at 1 bar. That's right. The outlet at 1 bar. Okay, at 1 bar. This is the outlet at 1 bar. And also the outlet at saturated. Okay, saturated, the temperature is 99.6. This is the saturated property. That's right, saturated property. Okay. For this case, we have sat liquid and sat vapor. For this is with vapor. Sat vapor is, 2,675. That's right. Okay, now you know entropy inlet, you know entropy outlet. That you substitute outlet, you substitute inlet. You substitute m dot is constant 2,000. That's right. You know m dot, you know entropy outlet, entropy inlet, and then convert the unit from hour to second. You get 292 kilojoule per second. Joule per second is what? We get 292 kilowatt. What does it mean? The work is positive. That means the turbine deliver work is 292 kilowatt of work to surrounding. Okay, there is some example. Okay, I will conclude the general balance procedure. The general balance procedure is look like the mass balance. The first step, you have to draw and label the flow chart. You have to draw the flow chart. That's right. What is the known and unknown property in inlet, in outlet? That's right. And you have to be sure that the flow chart inputs all of information you need to determine the specific enthalpy of each component. That's right. And also you have to specify inlet, outlet, temperature, pressure. And then show the state of application, liquid, vapor, or solid. That's right. And then you have to check material balance. If not balance, you have to do the material balance, follow the step as you studied before in the material balance. And then you take the energy balance. This is the general step for the energy balance procedure. Okay, look at the first example that we talk about the energy balance. For this case, we have two streams, mix two streams of water, mix to form water before feed to boiler. That's right, water. This two streams feed to boiler. We have a boiler. Boiler is to heat up the temperature and also change the phase. That's right, change the phase. The first stream, you know, mass of the first stream, 120 kilogram per minute of liquid water. And the second stream is 175 kilogram water per minute in liquid form. Okay, feed in liquid form. That's right. Outlet is vapor form. Okay. The temperature of inlet is 30. Outlet is 65 Celsius. Sorry. The inlet feed stream 1 is 30. Stream 2 is 65 and outlet is 17 bar. That's right, 17 bar. Okay, and also we know the steam boiler to this is the diameter of the pipe. Calculate the heat input because this boiler. The boiler we need the heat input to the system. That's right, we have to heat the boiler. We put the system, the outlet pipe diameter, you know. Pipe diameter, you know. Okay, from the temperature, you can estimate entropy from the steam table. You can estimate entropy from the steam table. I will show you on. Okay, and also pressure. You can estimate the entropy. That's right, entropy. And also you can estimate the temperature. For this case, okay, you know temperature. You can estimate from the steam table to find entropy. Okay, this from the steam table. From the steam table. This also from the steam table. Okay, the first step for that case, after you identify all known and unknown, and then you use the known condition to find the property from the steam table. Okay, you list all of this that you know. And also, the first step you have to do the material balance. For this case, material balance is only balance input equal to output because this is a steady state system. It's an open system. The input equal to output 120 plus 175 equal to 295. Okay, this mass balance. The second one, determine the enthalpy. For this case, we specify already. We specify enthalpy of inlet and outlet. That's right, in inlet and outlet. Inlet is 30 Celsius and the second stream is 65 Celsius. And also the outlet is steam at 17 bar for saturated steam. Okay, you label all of it. You label all of it. And also for the inlet, we don't know the pressure. We don't know the pressure. For this case, we can assume the property is independent of the pressure. That's right. The property independent of pressure. Okay, don't worry about it. Okay, the third step, you apply the energy balance equation. That's right, energy balance equation. Okay, you use this the general energy balance equation. Right. For this case, there is no moving the part of the system. Okay, sharp work, zero. And there is no the difference between the position of inlet and outlet. Okay, you can estimate the EP equal to zero. That's right, EP equal to zero. Okay, finally you get Q equal to delta S plus delta EK. That's right. S plus equal delta D EK. EK. Right. Sorry, EP. WEP. You get Q equal to delta S plus delta EK. Okay, next you have to calculate delta S. Calculate delta EK. Delta S should be summation of MI SI of outlet and not MI of SI inlet. We have two inlets. You know M of the first stream of water, M of the second stream of water. And also you know the entropy. That's right. You know the entropy. I need to know entropy. At the outlet, also you know the mass flow rate, you know the entropy. You get delta S. This is the delta S of the system. And then you estimate delta EK. Right. Delta EK is the kinetic energy. Also from this, you can open from the steam table to determine the specific volume of vapor or substrate to get this value. Okay. And also you divide it by the area of the pi r squared. That's how you know the diameter of pi is 6 and radius is a half of 6 is 3. That's okay, this is the cross-sectional area of the pi. This area, the flow direction. And then you divide this, the volumetric flow rate. That's right. When not volumetric flow rate, specific volume by area. That's right. Right. Sorry, it's you divide this by the volumetric flow rate by area. That's right. You get this term. Okay, what is the specific volume for this? We use the specific volume, and then multiply by the mass flow rate. This is the mass flow rate, MV dot. That's right, MV, not MV dot. Okay, this term equal to specific volume, volumetric flow rate. Okay, volumetric flow rate. Okay, and then you divided this by the area. That's right. Divided by area. You get the velocity. And then you calculate delta EK. That's right. Delta EK of the outlet. Approximately mu squared divided by 2. Mu squared divided by 2. Like for the inlet, it's approximately 0. Delta EK outlet minus inlet, approximately delta outlet for that case. Mass flow rate. That's right. The velocity, and then the conversion unit, this conversion unit. Get it. Okay, now you know delta EK, you know delta S, you can calculate. That's right. Heat transfer to the system is positive, that's correct. That's right. That is correct. Because this is the boiler. That's right. This is the boiler. Okay, I will stop the class for today.